Welcome to Solutions Part 2. It says, why are chemists great for solving problems? They have all the solutions. Ha ha ha. The goals for this are that you be able to name and calculate the pH of strong acids and bases, that you be able to recognize and balance oxidation and reduction reactions, and that you be able to assign oxidation um, numbers. Now, this is a review from, I believe, Unit 10 from last year. We talked about it in terms of solutions, acids, bases, redox. It's mostly 10.2, 10.3, 10.4, but it's mostly review. So the first thing that you have is you have a precipitate reaction. Now, a precipitate reaction is one where you're mixing two aqueous solutions and it produces a solid. So we have a couple of different terms for it. You have a solution, and a solution is where you can't actually see any of the particles that are in there. You can't; they're all dissolved. It looks like it's a clear liquid. And whenever you mix two solutions and you end up getting a precipitate, that right there is where you have the solid that's at the bottom. The liquid that's left over is called the supernate. And just as kind of, if you can see the particles floating around there, we generally call that a suspension. And actually, most of the antibiotics that you take that are a liquid, like clavamox or amoxicillin that's a solution, it's not really a solution, it's a suspension. That's why you have to shake it up before you take the medicine. Most or all solutions are dissolved in there, so you shouldn't have to shake them up. Okay, next you have the solubility rules. Now you are expected to know the solubility rules moving forward. I can at any time just say, hey, which of these are soluble or insoluble, and it could be a quiz grade. But as a general rule, group 1 and NH4 cations are soluble. So those are your positive 1 cations. Your acetates, your nitrates, and your perchlorates are soluble. Your bromides or chlorides and your iodides are soluble. Your sulfates are soluble, except when they're formed with calcium, strontium, and barium. Salts containing lead, mercury, and silver are generally insoluble, although there are some exceptions. Carbonates and phosphates and sulfides and oxides and hydroxides are also generally insoluble. You do need to know those rules that you were given at the beginning or for your summer assignment. Those are the expectation that you know them by now. Okay, so a metathesis reaction is another way of saying a double replacement reaction. It's called a metathesis, sometimes it's called a precipitate reaction. Whenever you do this, as always, you identify the ions, you write the product. Whenever you write the product, you're looking for conservation of charge. Okay, so something like this wouldn't work because barium has a +2 ion and chlorine has a -1 ion, so that doesn't balance in terms of charge. So you'd have to write it as BaCl2. Then once you do that, you have to check the solubility and then balance the equation. Now the reason why you have to check the solubility is for a metathesis reaction to actually occur, one of the products, at least one of the products, must be a solid or insoluble, okay, in order for the reaction to proceed. And then you would balance the equation according to the conservation of mass. You have something that's called a net ionic equation. If you look right here, you're taking calcium sulfate and barium nitrate, and you're mixing them together to get barium sulfate and calcium nitrate. Now that right there is an equation that represents this reaction. Now if you were to look at it in terms of a complete ionic equation, what you do is you write it in terms of ions instead of in terms of the salt. So instead of calcium sulfate, you write it as calcium ions and sulfate ions. Instead of barium nitrate, you write it as barium ions and nitrate ions. And you actually see that right there. So the complete ionic equation is everything that's there. Now if you look, you can see that I struck through certain things. Like I struck through that and I struck through that. And the reason why I did that is because that's on both sides of the equation. Now it really shouldn't be struck through for a complete ionic equation. Everything should be there. Now the question is why did I not write this in its ionic form? And that's because it's a solid. Anytime you have a precipitate, you can no longer think of those things as aqueous. They're not floating around in the solution. The reason why we write these as the ions is it's not really calcium sulfate that's in the solution. You have calcium ions that are floating around and you have sulfate ions that are floating around. So to say that it's calcium sulfate is really not accurate. It's calcium ions and sulfate ions. Now, when the barium and the sulfate are together, they are actually together. They are the solid that forms at the bottom of the container. So because of that, you actually have to write it as the solid. So the net ionic equation, you'll notice, is just the solid and the ions that go to the solid. Okay, whatever you had that's not part of the solid product is not in the net ionic equation. Um, the AP test is they tend to at least ask one or two of these in the free response each time is write the net ionic equation for this reaction. So Developing. Write a net ionic equation for silver chloride reacting with potassium sulfate. So in this case, you would say, okay, silver chloride. With silver chloride, you generally should specify, you should say silver 1 chloride, but it's almost always silver 1, so a lot of times they don't. You would write plus potassium sulfate, and then you'd write the reaction. You'd say I'd get AgSO4. You'd have to put a 2 there to balance the charge. Then you'd have to write plus 2 KCl and write it like this. At this point, that represents your chemical equation, your balanced chemical equation. Actually, I need to put a 2 there. But if I want to write a net ionic equation, I need to do something a little bit different. So instead of doing that, I'm going to write 2 Ag plus 2 Cl minus plus 2 K plus SO4 2 minus. That represents the one side of the chemical reaction. That's our reactants. Now on the other side, you would write Ag2SO4 because that is a solid precipitate. Plus, you would have 2K plus 2Cl minus. At this point, you have to identify everything that's the same on both sides. So you'd say, look, I've got 2 Ags here. Nope, no 2 Ags there. So I've got 2K pluses, they cancel out. I've got 2 Cl minuses, they cancel out. So my net ionic equation would be 2 Ag plus SO4 2 minus goes to Ag2SO4. Next it says write a complete ionic equation for aqueous copper reacting with silver sulfate. Whenever you have aqueous copper, that's just copper ions. We'll call them copper 1 ions because it doesn't specify, plus silver sulfate. You have AgSO4. And at this point, you'd say, okay, well, then you'd get copper sulfate plus silver. The problem is that this right here is not a solid, okay, and neither is this right here. So because of this is a tricky question. It would be no reaction. You have to watch out for these things when it says to write a reaction when no reaction actually exists. So next, acids and bases. You should be familiar with the definition of an arrhenius acid. Arrhenius acid is just when you have an increase in the amount of hydrogen ions, specifically when water is added. Whenever you have a Bronsted-Lowry acid, it means you donate a proton to another molecule. So there's not necessarily free ions for a Bronsted-Lowry. It could be something like HA plus Na goes to NaH. See how there's no free proton there? It's actually connected to something else. And Lewis acids have to deal with electrons. Now we're going to talk about the definitions of acid. It's in a lot more detail whenever we actually talk about acids and bases. You do need to know how to name acids, and it's all named based on the ion. So for example, if you had sulfate, which sulfate is SO4 2 minus, then to name the acid with SO4, you use the fact that it's sulfate and it becomes sulfuric acid. Okay, it goes to 8, us goes to ite, hydroric goes to ide. So as an example, if you had, let's say, H4C. Okay, this right here is the ion carbide. So this would be called hydrocarbonic acid. Okay, acid strength is measured by the dissociation of the proton. So whenever you have a free proton, that's considered to be a strong acid. Now, one thing that you need to be recognized is as the concentration of H plus goes up, you have a strong acid. So when you have a concentration of H plus that goes up, that's a strong acid. But now the problem is this: the pH actually goes down as H plus goes up. Okay, because it's a logarithmic relationship, you have this negative log. As one goes up, the other goes down. So if I have a low pH, I have a lot of free hydrogen ions. If I have a high pH, I have a low number of dissociated protons. Low pH, high hydrogen concentration is a strong acid. And here, these are just some comparisons. Like battery acid has a relatively low pH, so because of that, it's going to have a high hydrogen concentration. Where you get to water, water is considered to be the middle, and then you go on and see blood and sweat and bleach and all that kind of stuff. So you can just see for comparison value what those are. Okay, now acid dissociation, A strong acid is considered to be 100% disassociated at 1 molar. Now, when we say considered to be, a lot of times it's actually like 93% or 94%. But once we give the classification, we say it is considered to be a strong acid. That strong acid is 100% disassociated. We don't treat it any other way. So we have HClO4, which is perchloric acid. You have chloric acid, you have hydrochloric acid, you have sulfuric acid, you have nitric acid, you have hydroiodic acid. We're actually missing hydrobromic acid, okay, from one of them, and it looks like we might be missing one more. No, I think that might be it. Okay, so once you have these, you do have to memorize them. Whenever we say acid dissociation expression, there's two things that we're talking about. This is the equation or the expression that shows the dissociation. And this right here is called the equilibrium constant. We'll talk a lot about more of this in detail. This really comes into play with weak acids, not really strong acids. And the reason being is this term is actually 0 for strong acids. Strong acids are 100% disassociated. So if you were to put a 0 right there, anything divided by 0 is going to be infinity. So it doesn't make any sense. So whenever we talk about a strong acid, we tend to not talk about this Ka term. This Ka term is almost exclusively with weak acids. Now, a base. A base is kind of thought of as the anti-acid or the opposite of an acid. And that's not a bad way of thinking about it, just because they do neutralize each other and turn into water. But it has to do with the Arrhenius definition is the amount of hydroxide that is in a sample whenever water is added. Whereas Bronsted-Lowry still has to do with whether something can accept a proton or donate a proton, and Lewis has to do with donation or acceptance of electrons. So like I said, we're going to go to these in a lot more detail when we talk about acids and bases, but for now, this is what we're talking about when we're talking about a base, that there's a hydroxide. Now, when we talk about the strength of a base, we tend to do it in terms of the pOH, which is very, very similar to the pH. You had pH is equal to the negative log of H plus, just like you have pOH is equal to the negative log of OH. Anytime you put a P in front of something, it just means take the negative log of. Like you'll see pKa later, well, that just means take the negative log of Ka. If I say pKw, it just means take the negative log of Kw. Okay, so that P just means take the negative log of. So it's very similar. You have the strength of the base is related to the more hydroxide, the lower the pOH, and so on. Now, you also have the same base dissociation. You have 100% is considered at 1 molar. These are all considered to be strong bases. Just as a shortcut, I generally consider it to be everything, it is everything in group 1. And then everything in group 2, we tend to say for the most part is a strong base. Technically only strontium and barium are. A lot of times we'll consider calcium hydroxide to be one. It just kind of depends. This whole cutoff of what's a strong base and what's not, it's more of a continuum than a hard cutoff. And once again, KBs are really only useful whenever we talk about weak bases. So equating pH and pOH. So pOH and pH are based on the dissociation of water. So if you have a water molecule, it can split up into an H plus and an OH minus. So you should, in theory, if water's all by itself, have equal amounts of both. And they've actually done lots of measurements. They've found out that any normal water is going to have 1.0 times 10 to the minus 7th molar H plus and OH minus. So because of that, it's a relatively small value, but because you have the same amount of each, when you take the negative log of this number, you get 7. When you take the negative log of this number, you get 7. So you have 7 plus 7 is 14. So our entire pH scale is based on the idea of water going from 0 to 14. So the assumption is that if you have a pH of 0, you have to have a pOH of 14. If you have a pH of 14, you have to have a pOH of 0, and so on and so forth. Now, that artificially limits it to 0 and 14. You can have pHs that are higher or lower than 0 and 14, but that tends to be where most of them are centered. And you need to know this relationship that pH plus pOH is equal to 14. Okay, these right here are indicators, and there's no way that you need to memorize any of these or know any of them. But these are experimental indicators that change color whenever you reach a certain pH range. So in the lab, if you're going to use something like bromophenol blue, okay, bromophenol blue will actually change color somewhere between a pH of 3 and 4.6. So because of that, you can look for a color change at a certain point. Indicators are really useful if you can predict what you're looking for. So you're like saying, I have a solution. I want to know when it reaches a pH of 5. Well, if I'm looking to see when it reaches a pH of 5, I would choose an indicator that's somewhere around 5, that has its transition point between 5, and I'd want to make it as narrow as possible. So I'd probably choose something like bromocresol green. So it says, write and balance a chemical equation showing the neutralization of phosphoric acid with sodium hydroxide. So for this one, you need to know what phosphoric acid is. Because it's an ick, it is a phosphate. Phosphate is PO4. There's a 3 minus. So because of that, I'm going to need 3 protons. So I know that this is going to be H3PO4. Sodium hydroxide is pretty easy. It's NaOH. Now, in order for this reaction to occur, it's going to do a double replacement reaction. I'm going to go to Na, and I'm going to go to PO4. Now, this isn't a metathesis reaction. This is actually a neutralization reaction. So this product here does not have to be solid, but it can be. Okay, it doesn't have to be though. So we'll put solid question mark. Okay, and then the other product is going to be water, H2O. Because one of these H's is going to knock the sodium off, and the sodium is going to come over here. So we know we're going to have sodium phosphate. Now you know this does not meet the law of conservation of charge. Sodium is +1, phosphate's -3, so because of that you need 3 sodiums there. Okay, if you produce 3 sodiums, that means you need 3 sodiums over here, which means you're going to make 3 waters as well. So we have our balanced chemical equation. Now if you were to look at this, this should really be Na plus, and there should be 3 Na pluses plus PO4 3 minus. Now the reason, plus the waters. Now the reason why it should really be written as separate is because you have a aqueous solution that is an aqueous solution that is in water. Those ions aren't actually going to stick together. Okay, it says write a solubility product for the dissociation of acetic acid, and it tells you that CH3COOH. Now, a lot of times you'll see acetic acid written as HC2H5O2, but it's more commonly written as this CH3COOH. The trick is to not be hung up as far as where the H is and which H is which. You'll get into that more if you talk organic chemistry, but really the whole purpose behind this is you have CH3COOH, and you have to take one of those H's away because that's the definition of an acid. So now it really doesn't matter at this point where you take it away from, but the correct one to take away is this one. So you'd have plus CH3COO. Now to write a Ka expression, you should recognize that this right here is not a strong acid. So because of that, I'd write Ka is equal to H plus CH3COO over H CH3COO. Okay, and that's your disassociation expression and your equilibrium or your solubility product constant disassociation. Okay, next it says calculate the pH of a solution of 1 molar calcium hydroxide. And this was actually done on purpose because this is an interesting example. We're going to assume for calcium hydroxide that it's a strong base and that it disassociates completely. Now, the further you progress in chemistry, the more likely you are to say that this doesn't always happen, but it makes the question really, really complicated. So we're going to assume that it disassociates completely. So if this thing were to disassociate completely, I originally have 1 molar of this. Okay, and I have 0 of this, and I have 0 of this. Now, when this thing disassociates completely, that means it's going to end at 0, which means that I have to lose my 1 molar. Now, why is that particularly relevant? Well, I have 1 molar of calcium hydroxide. If one of these things falls apart, it's going to produce 1 molar on the other side. And it's going to produce 2.0 molar of hydroxide. Now, people always wonder, well, why does it produce 2 of that? If you look at the equation, this is a 1 to 1 to 2 relationship. For every calcium hydroxide that falls apart, whenever it falls apart, yeah, there's 1 calcium, but you have two hydroxides. So because of that, it's going to change. If this changes 1, this will change 1, this will change 2. So because of that, you end up at 0. This becomes 1, this becomes 2. You have your numbers right here. So the question says calculate the pH. Well, what I have is I have hydroxide. So for the hydroxide, I can solve for the pOH as being equal to the negative log of 2. Whenever you do the negative log of 2, you actually get a pOH value of negative 0.3. And people usually get weirded out by that, but whenever you have strong acids and strong bases, it is not abnormal for you to have negative pHs or pOHs. So now that I have the pOH of negative 0.3, the last step is, you remember you have that formula that says pH plus pOH has equal to 14. So if the pOH is negative 0.3 and this is 14, the pH has to be 14.3. Okay, in the next one it says oxidation. We're going to talk about this in a lot of detail whenever we talk about electrochemistry. But for now, you need to know that an oxidation reaction is one in which the electron is removed. So something removes an electron. So in this case, potassium has one electron normally, but now it doesn't have an electron. So because of that, there was one electron that was removed from the potassium that actually went to the chlorine, but you have that. Reduction is something where it gains the electron. In this case, the electron that potassium lost, right? Because we had one that it lost, so this electron was taken away, is actually gained. Was actually gained by the chlorine. Let's see if we can get this to. So since the electron was gained by the chlorine, it now has a charge that's negative. That's an example of a reduction reaction. Now, whenever you have a reduction reaction, you have to have an oxidation reaction and vice versa. So we call it a redox reaction. Okay, it has reduction, it has oxidation, they're mixed together. Because of that, you get this. You have zinc plus copper sulfate goes to zinc sulfate plus copper. So this is actually how you create a battery. So you have copper, you have zinc, you have solutions, you allow the electrons to flow back and forth between the wires, and that's actually what lights the light bulb or powers your cell phone or whatever it is you're trying to do. That's the redox reaction. Okay, whenever you assign oxidation numbers, there's a couple of rules that you have, and the first one is that elemental atoms are always 0. Now, elemental atoms mean if I have like barium by itself, and it's in its solid state, barium is going to have an oxidation state of 0. If it's O2, which is the elemental state of oxygen, oxygen exists as a diatomic because of Brinkelhoff, it's going to have an oxidation state of 0. Okay, if I were going to have something like, let's say copper in its elemental state would be 0. But if I were to mix copper with, say, nitrate, now it's not by itself anymore, so it's going to have an oxidation number there. Okay, the second one is monoatomic ions have the same oxidation number as their stable ionic charge. So you follow your trends. Lithium's going to be +1, calcium's +2, boron's going to be +3, carbon's iffy. We tend to not deal with carbon for the most part. And then nitrogen, oxygen, and fluorine are your -1s, and then your noble gases would be 0. Okay, for nonmetals, there's lots of rules. Okay, for the first part is the very first thing you would look at is you would tend to look at fluorine. Okay, I know that's C on here, but you would look at fluorine first because fluorine is always -1. It is the most electronegative element. Because it's the most electronegative element, it will always be -1. Always, always, always. Okay. Oxygen is always going to be -2 with the exception of you have peroxides. So if you were to have something like H2O2, now if oxygen were -2, you would have a total charge here of -4. The problem is that you can only remove one electron from each hydrogen. So because of that, you do have exceptions where you have things like peroxides. Okay, hydrogen is usually +1, but it can be -1 under certain circumstances. And then, like we said, we talked about fluorine. Whenever you add it up, the sum of the oxidation number for the neutral compound is 0. So for example, if you were to have something like NH3, okay, NH3, hydrogen can be -1, nitrogen can be +3, I have 3 hydrogens at -1. They add up to be 0, so ammonia has a charge of 0. Okay, the activity series can actually be predicted from this oxidation reduction reactions. And we'll talk a little bit more about this because we're missing a piece right here that tells us the energy. But that energy right there actually is used to predict the activity series. Now, the activity series determines whether a single replacement reaction will actually occur based on the energy, whether something is more stable or less stable. So that's directly related to this idea of oxidation numbers. Okay, so it says determine the oxidative state of sulfur and sulfuric acid. And it gives you a picture of what sulfuric acid looks like. And so you've got to say, okay, well, what's it going to be? Well, sulfuric acid is going to be H2SO4, which is a neutral compound. Since it's a neutral compound, now we need to be able to say, okay, well, what's the oxidation number of each thing? So we have our rules. Our first rule is there's no element by itself. Our next rule is there's no fluorine. Our next rule is that there's oxygens. I have 1, 2, 3, 4 oxygens. And our 4 oxygens at -2 apiece gives me a total charge of -8. And so now I've got to look and figure out a way that I can make this thing neutral. I have 1 sulfur atom, and I have 2 hydrogen atoms. Well, the 2 hydrogen atoms are pretty easy. Because I have a negative charge right here, I can assume that hydrogen is going to be +1. Because remember, it can either be +1 or -1, but it doesn't make any sense for it to be negative. So I'm going to say I've got 2 hydrogens at +1, which gives me a charge of +2. Well, that actually leaves me short. I need a +6 charge. And if you need a +6 charge, if you look at sulfur, sulfur is either stable by gaining 2 electrons or losing 6 electrons according to the trends on the periodic table. So because of that, you have your oxidative state here. You're going to have hydrogen is going to be +1, oxygen is going to be -2, and sulfur is going to be +6. Next, it says solution should be converted to moles and then reacted. It says, for example, you have 25 mils of 1 molar hydrochloric acid is neutralized with 52 mils of barium hydroxide. Determine the molarity of the barium hydroxide. So this is another example of a calculation that we're going to do later. But realize that you can't do calculations with molarities and volumes. Instead, you can only do calculations with moles, which is the basis of your balanced chemical equation right here. So really this should be 2, this should be 1, this should be 1, and this should be 2. And realize that this is a molar relationship. So what I have is I can say 25 mils times 1 molar is 25 millimoles. If you don't like 25 millimoles, it's the same thing as 0.25 moles. Okay, finally you have 52 mils. The number of moles has to be equal for it to be neutralized. So you'd say, okay, well, if this is how many millimoles of hydrochloric acid I have to have the same number of millimoles of barium hydroxide. If you don't quite get that yet, it's a neutralization reaction. We'll get into that a little bit in class. That's it.